Hey pre-calc, welcome back. Our objective today is going to be to graph exponential as well as logistic functions. I've got the checklist on the screen. You know what to do from here. So I'd like for you to try this warm-up. Try to do as many of these as you can without a calculator. Hit continue when you're ready to check your answers. All right, answers are on the screen, so you can go ahead and pause, change anything that you need to. Just keep in mind that when you've got a fractional exponent, the denominator of the fraction is your root. The numerator is still your power, your exponent. When you have a negative exponent, it brings everything down to the denominator. And first pause on your screen, can you go ahead and copy what I have on my screen? So let's generalize these exponential rules. So if I have a to the 1 over n, then that means the nth root of a, right? If I have a to the negative n, that's the same as 1 over a to the positive n, so I can change the sign of the exponent if I change the location of the base. And then if I have both a negative and a fraction, that means I need a root and it needs to be in the denominator, right? So this is going to be 1 over the nth root of a. That's kind of in general our exponential rules. So we're going to be working with exponential graphs today. So we're going to be looking at graphs in this format, like y equals 2 to the x, so where your independent variable is in your exponent. Okay, so that's what makes this an exponential graph. So let's plot some points and kind of get a feel for what the general shape of these graphs are. So for example, if I put 0 in for x, well remember 2 to the 0, anything to the 0 is 1, so I should have the point 0, comma 1. Let's keep going on. If I plug in 1 for x, I should get 2 to the 1, which is 2, right? So I should have the point 1, comma 2. If I put 2 in for x, my y value is going to double, right? So now I have 2 to the 4, so I should have the point 2, comma 4. And then as I move on, my next output for my integer input of 3 is going to be, again, if I double 4, now I'm at 8, right? When x is 4, y is going to be 16. See how I keep doubling? And then I'll move myself here. When x is 5, I have a y value of 32. So exponential growth functions take this general shape here, all right? But let's take a look at what happens with negative x values as well. Remember that a negative exponent does what to my output? It's going to flip it, right? So if I have 2 to the negative 1, that's the same as 1 over 2 to the positive 1. So let's come over here to when my input was positive 1, my output was positive 2, right? So if I take 2 and I reciprocate it, I flip it, I get 1/2, right? So let's take a look at some of these. So when x is negative 1, my output will be 2 to the negative 1, which is 1 over 2. It's not negative 2. You see that? It's same output here, but just reciprocated, just flipped, okay? So now let's test when x equals negative 2. We'll go back to your output at positive 2, which was 4, and flip it. So we should get 1/4, right? What should we get when x is negative 3? We should get 2 to the negative 3, which is 1 over 8. And then if I continue to basically multiply by 1/2, you see we're getting smaller and smaller. We're just taking the y value we got for that positive input and taking the reciprocal, right? So instead of 5, comma 32, I have negative 5, comma 1 over 32, right? Notice that we are never going to get a negative output, okay, because I have 2, a positive number, to a power. Even if that power is negative, it just makes it a fraction, if you will. And will we ever reach 0? We will not. That's what we call an asymptote, right? So let's formalize some of the aspects we're looking at here. All right, I'm going to force a pause on your screen. Can you go ahead and put the parent function y equals b to the x? And notice again, your independent variable is in the exponent, which is what makes us exponential functions. And we've got one that's exponential growth, that's going to become that red function here, and then one that's exponential decay. Notice that they both go through the point 0, comma 1, and they both have horizontal asymptotes at y equals 0. So go ahead and copy the screen, and then we're going to fill in a few things together. All right, so for exponential growth, I'm going to grab my red pen here. This is when b is greater than 1, alrighty? And for exponential decay, this is when b is between 0 and 1. Okay, b is never less than 0. B is never negative, or you're going to get some funky things. You'll get non-real outputs, right? So let's talk about kind of what's the same, what's different. Do we agree that the domain for both of these is what? All real numbers, right? What about the range? The range is going to be 0 to infinity. Now, do you want a bracket on 0 or a parenthesis? I'll be a parenthesis, because remember we saw, okay, we're never going to quite get to 0, right? Good deal. Let's talk about the intercept. So what is the y-intercept for both? The y-intercept is going to be 0, 1, because when I plug in a 0 here, anything to the 0 power is 1, right? So you can see that we have that. And then let's talk about end behavior, okay? So we have this asymptote of the x-axis, which is y equals 0. So I'm going to put horizontal asymptote of y equals 0. So that's what I really want you to kind of focus on for a bit here. Notice that in both cases, whether you have exponential growth or decay, one of your tail ends is going to go towards 0. The other end is just going to go to infinity. Okay, so that's really important to kind of think about that end behavior. Again, one tail end goes to 0, the other goes to infinity, and it grows what we consider to be very fast. Okay, we've got this exponential growth, like when our base was 2, it doubled each time, right? If my base, if b is like 10, you're going to have this same general shape, but it's going to be even steeper, right? The larger b is, the steeper the growth, the steeper the graph. But the general shape is the same no matter what your b value is. All right, you don't need to write anything yet on this. Let's try and do a review of transformations. If I add or subtract a number on the inside or outside, what does that do to the function? That shifts the function, right? That is a vertical or horizontal shift. What if I multiply? What does that do? That's going to be a stretch or a shrink. And what if I multiply by a -1? That is going to be a reflection, right? So I'm going to force pause on the screen. See if you can you don't have to write these down unless you feel like you need the review, but if you feel like you've got it, see if you can kind of mentally answer each one. Again, you don't have to write it if you think you've got them, and then when you're ready to check, hit continue. All right, here are my answers. I just want to make a note here that I put vertical stretch or shrink for sieving on the outside, but shrink stretch for sieving on the inside. Remember that it's a vertical stretch if c is greater than 1, shrink if c is between 0 and 1, vice versa for horizontal, right? Because remember, for horizontal, you have to think, what do I have to do to get x by itself? Because everything is already solved for y. So that's why inside is always opposite. All right, force pause on your screen. Can you go ahead and copy f of x in your notes for me? Okay, so let's try example 1. It says, how is the graph of f of x equals 2 to the 3x minus 1 transformed from y equals 2 to the x? So how many transformations, first of all? There's 2, right? There's this 3 inside the parent function, right? That's inside the exponent. And then this -1, is that inside or outside? That's outside. See how it's not in the exponent? It's on the outside. So the 3 is going to be a vertical change or a horizontal? That is going to be horizontal. So is that a stretch or a shrink? That is a shrink. So we're going to put horizontal shrink because 3 is greater than 1, right? And inside is opposite. Now, what does the -1 do? Which way do we shift there? We can go down 1. Okay, so that horizontal shrink is just going to kind of make the graph grow a bit faster. You can also think of a horizontal shrink as a compression towards the y-axis, right? So let's do a rough sketch here. Let's plug in 0 for x and see what we get for y. So if I do f of 0, I'd have 2 to the 0. Well, anything to the 0 is is 1, and then 1 minus 1 is 0. So now I have the point 0, comma 0. All right, so remember our original parent function had that y-intercept, right, at 0, 1. So see how we've shifted down 1, right? Where was the horizontal asymptote for your parent function? It was y equals 0, so where will it be now? Y equals negative 1. We've shifted down 1, right? Okay, are we in exponential growth or decay? This will still be growth. We haven't reflected, and my base is still greater than 1, right? So this is exponential growth. It will look roughly like this, okay? And then it says describe the end behavior, and we want to use limit notation, right? So that's when we do limit as x approaches infinity of f of x equals, so let's do this limit. This is the left tail or the right tail? This is the right tail. X is approaching infinity. So as we go to the right forever, what does y approach? Y doesn't approach anything in particular, right? Just goes up forever. All right, then we're also going to do the left side, the limit as x approaches negative infinity of f of x. Make sure you're paying close attention to this notation because I've seen some interesting things on, interesting notation on some quizzes. All right, so now as we go to the left forever, what does your y approach? Now it actually does approach a number, right? It approaches negative 1, okay? So before we had any transformations, our tail ends approached what two things? Do you remember? One approached infinity, the other approached 0. Now that we've shifted down 1, instead of 1 approaching 0, it now approaches negative infinity. Force pause on your screen. Can you go ahead and copy example 2? Okay, so it says graph the function and analyze. So let's graph first. Let's just plug in some points, okay? So let's start with 0. When x is 0, what is y? Y is 1, right? Anything to the 0 power is 1. Okay, now let's do some negative x values because a negative times a negative is ultimately going to give me a positive exponent, okay? So when x is negative 1, I get 2 to the positive 1, which is 2, right? When x is negative 2, what do we get? We're going to get 4. What do we get when x is negative 3? We will double even more, right? We'll get 8, okay? So you can see kind of this exponential piece here. Now let's try some negative, or some positive values, meaning we'll have a negative inside the exponent. So when x is 1, what do we get for our output? We get 2 to the negative 1, which is 1/2, right? What about when x is 2? We get 1/4, and now we just get closer and closer to the x-axis here, right? So we'll look something like this. All right, so you go ahead and fill out the domain and range for me and hit continue when you're ready to check, and continue. All right, domain is all real numbers. Range is 0 to infinity, but make sure that you have parenthesis and not bracket there because we're never going to quite get to 0, okay? We get infinitesimally close, but we never reach it. All right, would you say this function is continuous or not? It is continuous. I can draw that without picking up my pencil. Increasing or decreasing? This one is decreasing because of the negative exponent, so we've got some decay here. Any symmetry? No. And this is what we call bounded below by, what is that asymptote? Y equals 0. Any relative min or maxes? Any extrema? None. Any asymptotes? Yes, y equals 0, right? Okay, now let's write the end behavior. So I'm going to go limit as x approaches infinity of f of x equals, so this is going to the right. As I go to the right, what do my y's approach? My y's approach 0. And now let's do the limit as x approaches negative infinity of f of x. So this is as we go to the left. As we go to the left forever, the y's just go up forever. So this would be positive infinity. All right, well, exponential functions are great. A lot of things grow exponentially for a while, though, and then oftentimes they hit what we call an inflection point, and they start to kind of level off. And so oftentimes a more realistic model or equation for modeling populations is what we call a logistic function, okay? And there are kind of two formats of it. You'll see it in both ways. So before pause on your screen, can you go ahead and copy both of these parent functions for me in your notes. So what I want to bring your attention to is the exponential piece inside these parent functions, that piece right there, okay? And I want to kind of hark back to our exponential functions and think about the two tail ends. So picture an exponential function, could be growth or decay, doesn't matter. What are the two tail ends approaching? One's approaching infinity, right? And one's approaching 0. So let's see what happens to this whole function now that we've got this particular exponential piece. So we are looking at what happens at the tail ends, and that is going to give me my horizontal asymptotes if they exist, okay? So again, my exponentials have two tail ends. One goes to infinity, right? So when this goes to infinity, and that means that entire denominator is going to get huge, right? So when the denominator gets bigger and bigger and bigger and bigger and bigger, and your numerator is just this constant, as if you're dividing by a massive number, then the whole thing is going to approach what? Do you remember? It's going to approach 0, right? Because I'm dividing this denominator. As the denominator gets bigger, the whole fraction itself is going to approach 0. Right? So that's one of my horizontal asymptotes for logistic functions. Now, what does the other, think about exponentials again. They have two tail ends. One goes to infinity, the other goes towards what? Towards 0, okay? So I'm going to come back to this function, look at the box piece I have, I'm going to replace it with 0. So when I do that, I get c over 1 plus a times 0, because that exponential piece, when we're going to infinity, one tail end will go to 0, okay, because I'm just thinking tail ends right now, all right? So this becomes c over 1 plus 0, which is 1, which is c, okay? So that's why it says here, c is the limit to growth, because it is your second horizontal asymptote, okay? So you've got two horizontal asymptotes, and we'll look at a couple particular examples here so you can see. We've got two horizontal asymptotes for logistic functions, and they are y equals 0 and y equals c. So make sure you have those in your notes, and then let's try a couple examples. So I'm going to force pause on your screen. Go ahead and copy f of x for me. Okay, so we can tell that this follows our logistic function, right? This is a logistic function based off our formula here. So for horizontal asymptotes, well, we said it was y equals 0 and y equals c. Well, what is your c value here? It's 8. Okay, so those are your two horizontal asymptotes. For your y-intercept, how do we find that? We just plug in 0 for what? For x. So I'm going to find f of 0. So that's going to be 8 over 1 plus 3 times 0.7 to the 0, right? But what is anything to the 0? Anything to the 0 is 1. So my denominator becomes 4. So my y-intercept must be 0, 2. All right, let's take a look at this graph and see how we did. All right, so here's our logistic function graph. See this nice S shape. So you can see this exponential growth here. And now there's that y-intercept we found, right? This is called a point of inflection because we switch from concave up. See how that's curving up like a cup? And then we switch to concave down. Now, this is not changing the increasing, decreasing behavior, right? This is increasing on its entire domain, but the concavity does switch, right? We go again from concave up. You've got this exponential sort of piece, and then we start to taper off, okay? All right, now let's take a look at our asymptotes. We got y equals 0, which looks great, as well as y equals 8, which looks awesome as well. Force pause on your screen. Will you try example 4 on your own? All right, answers are on the screen. Go ahead and change anything if you need to, and I will see you all next time.